Hi everyone, welcome to our fifth lecture. This lecture is going to be on sound, and it's a combined lecture for both the calc and the non-calc students. There's no calculus involved in any of this. The lecture that you're actually going to watch was recorded last year at this time, but it had an introduction which was not applicable to this year, so I had to remove it. But other than that, the video quality was good, and so I thought I'd just recycle it. Okay, enjoy. So let's start off. What is sound, and what are some of the phenomena that it exhibits? Well, first, sound is a wave, and it's a wave in air. Okay, and it's a wave actually in the density of air. So there are areas of the air where the air is more compressed. So higher density areas, that's like a crest, and then there are areas of the air where the air has been rarefied, it's been pulled apart, so the density is lower, and those are like the troughs. And so basically, when you hear sound, when sound is propagating through air, it's creating these kind of compression waves with areas of high density and areas of low densities. I'll show you a diagram later, and that's how the wave propagates. Okay, the one interesting thing about sound is unlike the waves that we've mostly been thinking about before, although I didn't specify it clearly, is that sound waves are longitudinal waves, whereas many other waves, not all other waves, are transverse waves. Okay, and so what's the difference between these longitudinal and transverse waves? Also, this is important because longitudinal waves do not allow for polarization, whereas transverse waves do allow for polarization. And so there is a difference in terms of how these things behave, these waves behave. Okay, so let me start off by defining for you what transverse waves are. So remember that a wave is made up, a wave travels through a medium, and the medium can be thought of as being made up of these oscillators, which are coupled to neighboring oscillators. So if one oscillator starts to oscillate, it basically influences its neighbor. Okay, now when an oscillator oscillates up and down like this on a string, it produces a wave. Actually, let me just show you the diagram below here. Okay, so when this oscillator here is oscillating up and down like that, it produces a wave by influencing its neighbors, which will oscillate up and down. But the wave travels to the right in this diagram, whereas the oscillator in the string, and you can just follow it by putting a little dot on the string, is moving up and down like that. And if you take a look at the motion of the oscillator, of one oscillator in the string, and you take a look at the propagation of the wave, they're perpendicular to one another. Okay, and that perpendicular element is what makes a transverse wave. So basically, the definition of a transverse wave is if the oscillation of the particles in the medium is perpendicular to the direction in which the wave propagates, then you have a transverse wave. Again, for a string, you put a little dot on the string and you just watch what that dot does, and it'll oscillate up and down. Okay, but if you follow any one of the crests, that crest will move to the right, okay, at some constant velocity. All right, so those are transverse waves, and water waves are transverse waves. Electromagnetic waves like radio waves and so on, I'll show you in a minute, those are also transverse waves. So most waves, are transverse, but sound is actually a longitudinal wave. Okay, and so longitudinal waves, there the oscillation of the particles is actually parallel to the direction of the propagation. And you might wonder, how does that work? And so I've got this diagram over here. Okay, and this is a diagram which basically shows the sound traveling down a tube. Okay, so you can imagine like a tube of air. If you have a paper towel, that the cardboard tube in the middle, and you blow down the cardboard tube, and you can make a sound with it. So you can imagine the sound traveling down the tube, and if you could see the air molecules, what you would see is the sound is actually made up of like these regions where you could see the dots are closer together. These are regions of high density, where the air is slightly more dense than these other regions in between, which are low density. Okay, now if you followed any one of these high density regions, they would travel from the sound source over here, say that's where your mouth is, and they would just travel down the tube over here. Okay, like that. All right, so the wave is propagating to the left as it was in the previous diagram, but now if you take a look at any one of the particles here, it basically bounces back and forth like this. So the direction of the propagation is to the left, And the motion of any one of the air molecules is back and forth like that, also to the left and right, and you can see that they're actually parallel to one another. Okay, so if the oscillation is parallel to the direction of propagation, you have a longitudinal wave. If the direction of the oscillation is perpendicular to the direction of the propagation of the wave, you have a transverse wave. Okay, so waves on a string are transverse waves. Water waves on the surface of water are also transverse waves. So is electromagnetic radiation, and this is things like radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Okay, these are all wave phenomena of different wavelengths, and they're also transverse as well. Okay, now what electromagnetic waves are like, that's a little bit hard to understand. They're basically waves of electricity and magnetism, but you could still think of them as transverse waves. Okay, and this leads to this idea of polarization, and only transverse waves can be polarized. In 3D, you could actually have two perpendicular polarizations. And what does that mean? Well, I can't draw the whole wave here because this would be a very messy diagram. Okay, so basically what I have here is the direction of the propagation to the left, and what you could see here in the middle here is basically the direction in which the oscillation occurs. There's two possible perpendicular directions, okay? And what are they? Well, one is the oscillator can oscillate up and down like this while the wave propagates to the right like that, okay? Oscillates like that, and the wave. But another possibility, because of the symmetry of space, is that it could actually oscillate like this, and you still have propagation to the left, okay, or to the right, sorry, but this time it's in and out. Okay, so you can have transverse up and down, and you can have transverse oscillation in and out of the page like that, and these two are perpendicular to one another, like the in out is perpendicular to the up down, but they're both perpendicular to the direction of propagation. Okay, and there can't possibly be a third, because if there were a third, if there'd be oscillation perpendicular to both of those, then it would be longitudinal. All right, and that's separated out. So these two different ways of these two different possibilities for perpendicular, they lead to two different polarizations. Okay, and so this is actually how polarizing filters work with light. So I don't know if you've ever done any camera work, but there are these polarizing filters that you can put on the camera, and light, when it reflects off of a surface to cause a glare, say off of a table or off of like the surface of water, you get this glare, and the glare can be overpowering when you take a photograph, and the glare light that's emitted from the glare might be polarized this way. So here's the surface of the water, the light comes in and it basically bounces out like that. Okay, and now if you have a polarizing filter which only allows polarized light up and down, and it cuts out left and right polarization, well, then that gets cut out. Okay, and so with these polarizing filters, you can actually turn them on the camera. Okay, and by orienting them in such a way, you can either cut out the in-out polarization or the up-down polarization, and it actually can dramatically change the nature of the photograph that you're going to get, because if you cut out all the in-out polarization, then basically what happens is you get rid of all the glare, and it's suddenly, this water, the glare off of the water, which was overpowering, disappears. So this would be useful for diagnostic tools too. Okay, you can imagine if sound were polarized and you were using some kind of ultrasound diagnostic, you'd be able to differentiate the two polarized modes, and then you might get different imaging. But that doesn't happen with sound. Sound just doesn't have any kind of polarization, because it is a longitudinal wave, and longitudinal waves, I mean, you only have one direction, and that is parallel to the oscillation can only be parallel to the direction of the propagation. So you don't have two possible polarized modes as you do with transverse. So transverse waves and longitudinal waves, they have a qualitative difference. Okay, they're significantly different, and they behave differently. Okay, so again, with something like light, you can really filter out one polarization or another polarization, and if this were in the context of some kind of diagnostic tool, you might want the up-down polarization, and that would give you one picture of the body or whatever you're doing the diagnostic on, or you could choose the in-out, and it would give you a different picture, and that might give you different information. But there's nothing like that for sound, and so like ultrasound, there's no polarization in that at all. Okay, so that's one property of sound waves. They are longitudinal waves. The next thing we're going to study about there's nothing but qualitative. There's really no formulas in that part. But the next thing we're going to study is intensity. Okay, and all waves carry energy with them. All right, but we're again, I'm going to focus on sound, okay? And in 1D, that energy really can't diffuse because the energy is kind of constrained to travel along the one direction with the wave. But in 2D and 3D, the waves, the crests, they form like spheres, and the spheres get bigger and bigger and bigger as the sound goes out. Okay, I've got a picture of it below. And so you can imagine that if you have like an alarm and it produces a crest, the crest is first, a small little ball, a small little sphere, and then the sphere gets bigger and bigger and bigger as the wave propagates out. Now, what happens there is the amount of energy on any one of those spheres is constant because that was the energy that was given by the alarm at, say, t equals 0 when the crest was first born. But that energy, say 10 joules, that energy stays the same. But now that energy is being smeared out more and more over a larger and larger surface area for the crest. Okay, and so what happens is that as you get further away from the sound source, it becomes quieter. Okay, and so you might want to say, well, can I measure that? Is there a way of measuring how the how quieter something is as I get further and further away, or how louder it is as I get closer? And the quantity which does that for you is called intensity. Okay, and so we're going to take a look at the intensity, and that's this formula in the box right there. This is actually the definition of the intensity. The intensity is how much energy the wave deposits per unit area per unit time. Okay, so let's get our heads around this equation. How do we understand it? Let me first say it in terms of energy, and then I'll try to give you an analogy in terms of rain. If you wanted to measure, say, the intensity of a shower, like a rain shower or something like that. So how does that work? Well, obviously, if you're capturing energy, all right, the longer you wait, because the wave just keeps depositing energy and then more energy and then more energy and then more energy, the longer you run your experiment, the more energy you're going to capture. Okay, so the amount of energy that gets deposited obviously depends on how long you run your experiment. And so to get an accurate measure of the intensity, you don't want the time that you ran the experiment to be part of that, to factor in, so you divide that out. Okay, so one of the things is you have so much energy, and you don't want just the energy that's deposited, but the energy that's deposited per unit time. Okay, and that gets you a little bit closer to this notion of intensity. But that's not all there is to it. There's something else too, and there's this area here, okay? And the reason is because how are you going to capture the energy, right? So suppose you have something like, like a little square area, and the energy is being deposited onto this square area, like say a speaker, okay, or a microphone. Okay, so the microphone is actually capturing that energy. Now, if the microphone has a very small area in which it captures it, well, then it's just going to capture less energy, even for the same amount of time. The bigger the area in which you're trying to capture the energy that's being deposited, the more energy is deposited per unit time. And so the other thing you want to factor out is A. Okay, now if that was a little bit abstract, I've got an analogy here, but it's a very good analogy. In fact, you can talk about the intensity of rain, and let's see how we would do that experiment. Say you want to measure how much intensity there was in the rain last night. Okay, so what you would do is before the rain showers, you would go out and you'd put a bucket out. Okay, now if you have different size buckets, like you have a small bucket with like a small mouth and have a big bucket with a big mouth like that, you put these two buckets out. Obviously, for the same amount of time, the bucket with the bigger mouth will collect more water than the bucket with the smaller mouth. Okay, so you put both buckets out, you just wait 1 hour and you see how much water is collected. The bucket with twice the area is going to collect twice as much water. And so that doesn't seem fair. You want them to, give you the same measurement because the rain intensity was the same for both buckets. And so what you need to do is to divide out the area. Okay, but that's not all. it's also the amount of time that you left the two buckets out. So this time, imagine that you have two buckets and they have the exact same amount of area. Now, if you put them both out for the same amount of time, they'll collect the same amount of water. But if you put one out for 1 hour and you put another one out for 2 hours, the one for 2 hours is going to collect twice as much water. And so again, you want to be fair here. You say, well, the intensity was really the same for both buckets, so we need to divide out how much time we were collecting the water. Okay, so of course for waves it's energy. So for the energy, you look at how much energy is deposited, but you got to divide out the net that's capturing that energy. Okay, like the bigger that area is, the more energy you're going to collect. So you have to divide out that area. And also, the longer you wait, the more energy you're going to collect. And so you have to divide that out too. Okay, so if you divide out both the area and the time that you've collected the energy, then you basically have the measure that we call intensity. All right. So how does this intensity change over distance? Because after all, that's how I introduced this. I said, if you're up close to a sound source and you hear the sound, it's going to be louder than if you get further away. And it turns out that intensity follows this law called the inverse R squared law. Okay? And what does it mean? What does it say? It says basically that the intensity of the sound decreases as 1 divided by the square of the distance from the source. Okay, so let's try to make sense of that. So imagine here that you have a sound source. There it is. There's our sound source. Okay, and the sound source, it could be like an alarm or whatever. And what the sound source is doing is it's pulsing and it's creating these density waves, sound waves, and it creates a small crest, and then that crest grows. And then it pulses again and it creates another one inside of it, and then it creates another one. Now I've only gotten 2 drawn here, but you can imagine all these concentric spheres, each one bigger than the other by a distance lambda, and these are the crests that travel out. Okay, so this sphere that you're seeing here, of course I can only draw a circle because this is 2D, but you have to picture it as kind of a sphere. This crest of the wave is basically generated by the sound source, and it's a sphere. Okay, the total amount of energy on each one of these spheres is the same. So this small sphere has the same amount of energy as the bigger sphere, has the same amount of energy as the bigger sphere yet. And that's because when the sphere was created, when that crest sphere was created, there was only so much energy given to it, and that energy just got smeared out more and more and more over a larger and larger area. Okay, so the energy is uniformly distributed over that surface, and you may remember this formula. If you have a sphere of radius r, then the surface area of the sphere of radius r is 4 pi r squared. Okay, so if you don't know that formula, there it is. But basically, if you have a sphere and its radius is r, then the surface area of that sphere is 4 pi r squared. Okay, so now if we plug that area in to the equation above, remember our equation here was the energy deposited divided by the area times the time over which you're going to deposit it. If you plug that in there for that A, you get this 4 pi r squared, but it's in the denominator. And so if you forget about all the other factors, you could just see that the intensity is going to be proportional. That symbol just means proportional to 1 over r squared. Okay, so that means that as you go out further, the intensity will drop. But it doesn't drop as 1 over r, it actually drops as 1 over r squared, okay? And so the implications of that we'll see as we when we do a problem. All right, so this is sufficient for you to understand the inverse r squared law, but it's kind of hard to use this as in a formula for solving problems. So here's a different way that you can think of the inverse r squared law. If you have an intensity I1 at a distance r1, and you have a density I2 at a distance R2, these must be related by this formula. I1 over I2 is equal to R2 squared over R1 squared. Okay, notice it's 1 over 2 on this side, but it's 2 over 1 on the other side. It's flipped, and that's because it's inverse and also squared. So it's inverse R squared. So once again, I1 over I2 is equal to R2 squared over R1 squared. Okay, so one more thing before we actually jump in and do a problem, because now we can do problems with this formula. Let's look at the units of I, and the units of I are of course the units of energy divided by area, units of area, and units of time. And units of energy are joules, area is meters squared, and time is seconds. And so The intensity is measured in joules per meter squared second. But there's another unit that I want to introduce right now because we're going to see it later in the course anyhow, and it's the unit for power. A joule per second is given the symbol watt, W like that, okay? So when we get to electricity, we'll actually see that a joule per second is actually a unit of power, and it's given the symbol W, and it's called a watt, okay? So a watt is equal to 1 joule per second, all right? And you know what watts are because I'm sure you've bought light bulbs, and you know that light bulbs come in like 100-watt light bulbs and so on. Although now with the diode light bulbs, you're at much lower wattage, which is good because they consume less power. But if you had the old incandescent light bulbs, like a 100-watt light bulb, what does 100 watts mean? It means that that light bulb is going to burn up 100 joules of energy every second. Okay, and the human body actually generates heat because we metabolize our food, and the human body actually acts like an 80-watt light bulb. So basically, human body loses 80 joules of energy per second. Okay, now that's of course, you know, if you're just sitting and standing still or whatever, not being active, because that number can get very higher. But that number is giving you a sense of just how much food is being metabolized per second. About 80 joules of food energy is being used up per second. Okay, so let's do a problem with this formula right here. Okay, the inverse R squared law in this particular form. And so over here I have a sound source which is found to emit a sound of intensity 5 milliwatts per meter squared. A watt per meter squared is pretty big. Okay, that's pretty loud. So this is usually measured in milliwatts. So once again we have a sound source with intensity 5 milliwatts per meter squared, and that's at a distance of 1 meter. Okay, now if you heard 5 milliwatts per meter squared at 1 meter, what would you hear at 2 meters? What intensity would you hear at 3 meters? What intensity would you hear at 4 meters? What intensity would you hear at some arbitrary distance? Okay, so well, let's do that. If we use our inverse R squared law, we can identify I1 as 5 milliwatts per meter squared at a distance of R1, 1 meter. Okay, and we want to know what the intensity is. I2 at a distance of 2 meters. So R2 is 2 meters. Okay, so if we take this formula, and I'm just going to rearrange it, and I might have skipped a few steps here, but basically all I did was I just did some cross multiplying. I multiplied both sides by I2, and I divided both sides by I multiply both sides by R1 squared over R2 squared, and it basically just rearranges into this formula here. Okay, and I'm sorry, there should be a 1 right there, but I can just tell that I dropped the 1. All right, but nonetheless, I think it's pretty clear. So now if we say I2 is equal to R1 squared divided by R2 squared times I1, if we plug in our numbers, we have 1 squared over 2 squared times 5. 1 squared over 2 squared is a quarter. A quarter of 5 is 1.25 milliwatts per meter squared. Okay, really the number that's interesting is that 1/4. All right, so now let's do this at 3 meters. At 3 meters, we're not going to have 1 over 2 squared. We're going to have 1 squared over 3 squared, and that's 1/9. Okay, and if we did this at 4 meters, we'd have 1 squared over 4 squared, and that's 1/16. And so what you're noticing is an interesting pattern here. Okay, so this is really what you should appreciate about the 1 over R squared law. When you're at twice the distance, it's not like you're at half the intensity. You're not half the intensity at twice the distance, but a quarter of the intensity. So you double your distance, you 1/4 your intensity. Okay, you triple your distance and you're at 1/9 the intensity. You 4 times your distance, quadruple your distance, you're at 1/16. 5 times the distance, you're 1/25. Why? Well, because it's 1 over 2 squared. It's the distance squared. It's 1 over 3 squared. Okay, and the 1 over 16, that's 1 over 4 squared, or 1 over 5 squared for 1 over 25. And so basically it's 1 over the distance squared. Okay, and so the drop off is much faster than if it were something like linear. Okay, so there's the story with the inverse R squared law. These are pretty easy problems, so one example is sufficient. Now, the last thing I'm going to say about the 1 over R squared law is we were thinking about it in terms of sound, but it actually applies to all waves that expand in 3 dimensions, okay? Because whenever a wave is expanding in 3 dimensions, it's smearing its energy over a sphere, and the area of the sphere is decreasing or is increasing as 4 pi r squared, and so the intensity is decreasing as 1 over r squared, and hence the inverse r squared law. It actually even applies to particles. So like radiation, like radiation therapy that you might have in a hospital or whatever, radiation, it's just particles. They're like little alpha particles or beta particles. These things just go flying off in every direction. Well, in the radiation, when radiation occurs, the particles just fly off in all directions randomly. So it's not like they're all flying off to the right or to the left. They'll all just kind of spray out uniformly in all directions. And even though they're particles, the intensity of the radiation also drops off as 1 over r squared, because the uniform particles are now uniformly distributed over a sphere of radius r. Okay, and so as that r increases, the intensity will decrease as 1 over r squared. It's the exact same logic, but now being applied to particles that are spraying out randomly in in 3 dimensions. Okay, so there's a story with the inverse r squared law. The next thing about intensity is that intensity, especially when it comes to human hearing, spans a very, very large range. Like, it's actually quite amazing how quiet we can hear and how loud we can hear. Okay, and so we're actually in a situation with hearing that the hearing goes over many orders of magnitude, that is many powers of 10. And that's a little bit hard to get your head around, this idea of many different orders of magnitude. So let me try to describe it to you. Okay, basically, it's not so much that we're worried about like the number as the exponent. All right, so the quietest possible sound that the human ear can hear is 10 to the minus 12 watts per meter squared. Okay, so that's like a pin dropping, the quietest possible sound you could hear. Okay, and I know everyone's different, and your hearing probably decreases with age and so on, but roughly, this is correct. Okay, it's 10 to the minus 12 watts per meter squared. Well, human speech has an energy about 10 to the minus 6 watts per meter squared. Okay, and that's a million times louder. So when you're speaking, you're actually speaking at a sound intensity which is a million times greater than the sound of, say, a pin dropping. All right, and when you go to a concert or something and you've got loud music playing, then the intensity is actually like 10 to the minus 12 watts per meter squared. Okay, and whoops, okay, 10 to the minus 12 watts per meter squared. All right, and so you're basically jumping over many orders of magnitude there. All right, so how do you get that all into one scale? And well, that's the only way to do that is really with this thing called a log scale. But before we jump into a log scale, let me try to describe to you where log scales become useful. Okay, so hold on here. All right, so let's take the example of money. All right, so if you're a millionaire, all right, you have like $1 million or $2 million or $5 million, you're considered a millionaire. All right, if I give a millionaire $1,000, it really doesn't make that much difference. It doesn't change him from a millionaire to a billionaire or anything like that. If you're a millionaire and you get $1,000, you're still a millionaire. If you're a millionaire and you get $5,000, you're still a millionaire. If you're a millionaire and you get $10,000, you're still a millionaire. It's like if you're adding money in units of thousands and you're in the millions, you're not really making that much of a dent. It's still something. It does add a little bit, but it really doesn't push you out of the millionaire bracket. Okay, to really start pushing someone out of the millionaire bracket, you got to start giving them money which is in the millions. Okay, so if you have only $1 million and someone gives you another $1 million, well then you really feel that as a big difference. But if you have $1 million and someone gives you $1,000, that doesn't make that much difference. Okay, you'd still take it, but it doesn't make that much difference. All right, so in order to start bumping a millionaire, you have to be in the millionaire range. Okay, but a millionaire is nothing compared to a billionaire. So if you were to give $1 million to a billionaire, you wouldn't budge them at all. Okay, so if you're in the billion bracket and someone's working in the millions, that's just chump change to you. It's not a lot of money. Okay, of course it seems to a lot of money to us because we're not working in the million range, we're working in the thousand range. All right, so if you're only in the thousands range and someone gives you, $1,000, well, then you would appreciate it. But if you're a billionaire and someone gives you $1,000, it's nothing. Okay, if you're a billionaire and someone gives you $1,000,000, it's still pretty much nothing. You have to be given money in the billions range in order to be affecting a billionaire. And so really what you're looking at is not so much whether you're 1 billion or 2 billion or 3 billion. You're just looking at the billion part, because that's your like monetary range. Okay, so let's see how to do that. Okay, and whoops. All right, so the log function is really useful for this kind of thing. Okay, so the log function, the way it works is it basically, we're going to work with log base 10. I'm not going to say log base 10 every time. There are different logs, like log natural log, and there's log base 10, log base whatever you like. So we're going to work in log base 10, but I'm just going to call it log for short so that I don't keep saying log base 10 over and over and over again. So, the log function is really good for this. Okay, so if we take a look here, if you do log of 10, that's just equal to 1. All right, so now if you do log of 100, that's basically just equal to 2. Okay, and if you do log of 1,000, that's basically equal to 3. So what is the log function doing? It's basically counting the number of zeros you have. All right, so if you have 1 0, you get 1. If you have 2 zeros, 1 followed by 2 zeros, you get 2. A 1 followed by 3 zeros, you get 3, and so on. Okay, now 1,000 can also be written as 10 to the 3. So really what's going on here is that the log is stripping out the exponent. Okay, so log to the base 10 of 10 to the exponent 3 strips out the 3 in front. In general, log to the base 10 of 10 to the a is just a. Okay, so the log there is grabbing out the exponent part. All right, you can actually generalize this. It's not just 1 followed by 1 0, 2 zeros, 3 zeros. It's more like the log can see how many digits are in your number. Okay, so if we did log 2, log 2 is basically equal to 0.3. You can do that on your calculator. Log 2 is equal to 0.3. That 0 tells you that you have 1 digit in there. The ones column, the number in the ones column, if you add 1 to that, that tells you how many digits you have. Okay, so here that 2 is just 1 digit, and so that the number over here in the answer in the ones column is 0. All right, now if you had 20, if you did log 20, you actually get 1.3. Okay, that 1 tells you that there are 2 digits here. Okay, now what if you had 3 digits here? Log of a 3-digit number is going to give you 2 point something. In this case, log of 200 is 2.3. And then what if you have 4 digits here? Well, log of a 4-digit number is 3 point something. Well, try this on your calculator. Log of 2000 is actually 3.3. You'll notice that the number in the 1/10 column here, the number after the decimal, 0.3, that's always the same. Okay, that actually has to do with the fact that this is a 2. But the number in the ones column, that 0, 1, 2, 3, that actually tells you how many digits there are in the number that you're taking the log of. And the number in the ones column is always 1 less than the number of digits you have. Okay, so for instance here, if you did log of 30, well, there are 2 digits there, so you know the number in the ones column is a 1, because that's 1 less than 2. Okay, so it's 1. And then followed by something, which is the log of 3, it's actually 0.477. So the log of 30 is 1.477. The log of 40, again, there are 2 digits, so you expect the number to begin with 1 point something. So log of 40 is 1.602. 50, it's still just a 2-digit number, so now it's going to be 1 point and then whatever. I mean, log of 60, log of 70, whatever, all of those things, as long as there's 2 digits there, log of 77, log of 35, log of 67, as long as there's 2 digits, the number will always be 1 point something. Okay, and so the log is kind of counting the number of digits that are in your number. All right, and so here it is in the, if you have 3 digits, you have 3 digits in your number, like 300, 400, 500, 600. Well, then the number in the ones column is going to be 2, 2, and 2, followed by whatever. Okay, and the whatever depends on whether it's 3, 4, 5, 6, or so on. So look at these numbers and compare them. The reason I put XXX there is just to say I don't really care what the decibels are. I really wanted you to just concentrate on that too. And again, the fact that log of the number is equal to 2 tells you that there are 2 plus 1, in other words, 3 digits in the number. So I can give you any number you like. Okay, I just picked the number here, 57,392. How many digits are in it? 1, 2, 3, 4, 5. There are 5 digits. So the log of that number will have 4. Begin with 4 point something, and sure enough, do it on your calculator. It's 4 point something something something. Okay, again, I really don't care about the remainder of that. I just want that 4 in front. All right, and so if you go back to our millionaire billionaire problem, it's kind of telling you the financial bracket that you're in. So if you did log to the base 10 of millionaire, well, a millionaire is in the millions, 1 million, 2 million, 3 million, 5 million, doesn't matter. Okay, but if you do log of millionaire, you get 6. 6 followed by something, but the 6 is the important part. Okay, and if you had a billionaire, if you're in the billionaire range, then log of billionaire, that's 9. Okay, and so the log is basically counting those number of digits, and it just kind of tells you what bracket you're in. All right, so to jump from one bracket to another, you don't add 10, you actually have to multiply by 10. You have to be 10 times bigger. So, a 10 millionaire would be at bracket 7. A 100 millionaire, $100 million gets you into bracket 8. And by the time you get to 1,000 million, which is a billion, then you're into bracket 9, and so on. So that's how log functions work, okay? And they're very useful for taking situations like this, where you have, numbers that are spanning many orders of magnitude. And many orders of magnitude, that just means powers of 10, okay? And so to get from the quietest sound to human speech, that's like a million. That's like multiplying by 10 6 times before you get to human speech. And then from human speech to live music, you have to multiply by 10 4 times, okay, 10,000 times, okay? So you're looking at basically these levels, which are factors of 10 above the previous level, all right? And so that's perfect for a log scale. Log scales are not just used for decibels, which is what we're going to study in a second, but log scales are also used in chemistry for pH. For those of you who are chemistry majors, you know that the amount of the concentration of H3O plus in water is basically a measure of how acidic it is, but and so we define decibels as basically a log scale. So beta, the intensity in decibels, is going to equal 10 times log to the base 10 of I over I naught. Okay, so what are all the components in that? Beta is the intensity, but it's the intensity measured in decibels. And it's given these kind of funny units written as dB. You can see it there right here. And it's hard to say what you really mean by units when in a log scale, but nonetheless, traditionally, people write the intensity as dB. So if you see an intensity with dB after it, you know that you're getting the intensity in decibels, which is this log scale here. Whereas if you see the intensity written as watts per meter squared, you're actually working with the intensity as we defined it above. Okay, so beta is this intensity in decibels. It's the log scale for the intensity. I is the intensity in watts per meter squared, and this I naught is actually a reference intensity, and it almost doesn't matter what you choose for that reference intensity as long as you're consistent throughout. In fact, for many of the problems that we're going to do, the reference intensity just drops right out anyhow. Okay, so what would we choose the reference intensity to be for sound? And so if we're talking about sound as it's being heard by the human ear, a logical choice for the sound intensity would be to choose I naught. For the reference intensity would be to choose I naught as 10 to the minus 12 watts per meter squared, because that is the quietest possible sound that humans can hear. Okay, so we could just say for all our purposes, whenever we're working with decibels with respect to sound, we will use the reference intensity to be I naught 10 to the minus 12 watts per meter squared. Okay, so why do we want to define this? Okay, the reason is because, again, remember that intensity, human hearing, spans many orders of magnitude, and that log function is basically going to start to bracket those different intensities for us. Okay, and so the quietest possible sound, that's 10 to the minus 12. Okay, and so the log function will pick that out, whereas audible sound, sorry, not audible, but human speech, that's 10 to the minus 6 watts per meter squared. And, that's a million times larger. And the log function will pick out that particular bracket, just like it was picking out the millionaire versus billionaire bracket. The log function in the decibel formula is going to pick out which bracket of sound range you're in. Okay, and I think that'll come out with this problem that we're going to do next. So the question is, what is the intensity of 2 alarm bells if the intensity of just one is 30 decibels? Okay, and so maybe another way to word that is, if the intensity of 1 alarm is 30 decibels, what's the intensity of 2 alarms? Okay, and part B is, what's the intensity of 4 alarms, and what's the intensity of 8 alarms, and then what's the intensity of 16 alarms. Now notice the pattern here. I start with 1, and then I go to 2, and then I double that to 4, and then I double that to 8, and then 16, and then 32, 64, and so on. So I'm actually increasing each one of the questions by twice as many as the previous one. All right, so the first thing we have to be careful with is a common error that's made with decibels, and that is when you double the intensity I, you don't double beta. Okay, that's not the way it works. So, you might naively say, well, if 1 alarm has an intensity of 30 decibels, then 2 alarms must have an intensity of 60 decibels. And no, that is not at all the case. Okay, it doesn't work like that at all. I works that way. All right, so if you had like 1 alarm was, say, 5 milliwatts per meter squared, then 2 alarms would be twice that, 2 times 5, which is 10 milliwatts per meter squared, and so on. But betas don't work that way, because betas are on a log scale, and log scales are not additive. So let's see how they work. So let's go through this this question with some care. We start off with the formula again, but now notice that I put over here, I have beta 1, so I'm putting a subscript there because I'm going to refer to just one bell. Okay, so I have beta 1 is equal to 10 log of I1 over I0, where I1 now is just the intensity of 1 alarm. Okay, and below I'm going to have I2, and that's going to be the intensity of 2 alarms, and I'm going to have I4, which is the intensity of 4 alarms, and so on. Okay, but let's just look at the intensity of 1 alarm. So for 1 alarm, we have that the beta was 30, okay, and there's 10 log, and I1 we don't know, but let's actually solve for I1. Okay, so let's plug in all the numbers and solve for I1. We could plug in for I0 there, but I really don't care. I don't feel like putting in the 10 to the minus 12 in there, so let's just leave that as I0. We could substitute a number there, so it is in principle a known value, but let's just solve for I1 here. Okay, so here we have 30 on the one side and 10 on the other side, so we can divide both sides by 10, and we basically get that 3 is equal to the log of I1 over I0. But now you wonder, how do I tease out this I1? And the answer is, well, you exponentiate both sides. Okay, so if you exponentiate both sides, here you have 3, and by exponentiation I mean take 10 to the base, 10 is the base, and then raise it to this number as an exponent. So 10 to the power 3, well, that's 10 to the 3 right here. And what happens on the other side is you have to remember that log functions and exponentiations are opposites of one another. So you remember how you have the tangent and the inverse tangent? They undo one another. And then there's like sine and inverse sine, they undo one another. And you can try this on your calculator. Take any angle, take the tangent of it, then take the inverse tangent of it, and you get back to the same angle you started with. And it doesn't work with just one angle, it works with any angle you want. So you take any angle you want, tangent, inverse tangent, you get the same angle back. Conversely, you could start with any number. You take the arctangent of that number, and then you take the inverse tangent of that number, and then you take the tangent of the number, and you'll get that number back. So tangent and inverse tangent, they just undo one another as if you did nothing. Okay, and it doesn't even matter which order you do them in. It's the same thing with the log and exponentiation. So if you take a look over here, I have A is equal to log to the base 10 of B. If that's true, then basically it means that 10 raised to the power A is just equal to B. So you can imagine that what you're doing is that you're exponentiating both sides with base 10, and so A becomes 10 to the A, and this side becomes 10 to the log to the 10. But exponentiating with base 10 and logging with base 10 undo one another, and all you just get is B. out, okay? And so if you have A is equal to log base 10 of B, that's the same as saying 10 to the A is equal to B. And that's exactly what I used here to get from 3 is equal to log I1 over I naught to 3 to the 10 is I1 over I naught, okay? So how did that work? Well, you see A here, A is like your 3, and B is your I1 over I naught. So when I exponentiate, instead of 10 to the A, I get 10 to the 3. Instead of B there, I just get I1 over I naught. And now I've teased out the I1. It's easy. Just rearrange. You get I1 is 10 to the 3 times I naught. And again, I could substitute in for I naught, 10 to the minus 12, but I'm not going to bother because I'm really not interested in that number. I just wanted to show you this to show you how you can like tease out that I1. Now, the I's are additive. So what that means is that if one alarm has the intensity 10 to the 3 I naught, then I2 is just 2 times that. Okay, so this part here is just for 1, and this part here is 2 of them. So because I's are additive like that. And so basically I2 is just 2 times I1. Well, we could have started with that, but again, I wanted to show you how you could tease out I1 out of the log function. Okay, so if you have I2, that's just equal to 2 times I1. All right. So now what? Well, now what you could do is you can say, all right, let's start here with instead of beta 1, beta 2. So what's beta 2 going to equal? Beta 2 is going to equal 10 log to the base 10 of I2 over I naught. And if we substitute in our numbers, you're going to get that that's going to equal 10 log to the base 10 of, instead of I2, I could just replace that with 2I1 like that. And now let me write that as 10 log base 10, 2, and that's not an x there, that's times I1 over I naught. Now the reason I did that, the reason I wrote it that way, is because the log has a very interesting property. And basically, it turns multiplication into addition. So what's happening here is you have two factors. You have this 2, and then you have the I1 times I1 over I naught there like that. And they're being multiplied together. So these are two factors like that. Well, let's just take that 10 and let's pull it outside. So we have the 10 there, open square bracket, close square bracket. Okay, so the 10 has been pulled out. It's no longer relevant for the next part. Okay, and we have the log. And now the log, what it does is it can actually separate that 2 from the I1 over I naught, and when it does, it actually changes the multiplication into addition. So log of 2 times I1 over I naught is just equal to the log of 2 plus the log of I1 over I naught. And this is a log identity, which you should remember from a previous class. If not, I'll remind you of it. It really doesn't matter whether it's base 10. We're working in base 10, but it could be any base. It could be the natural log or whatever. But if you have the log of A times B, that's just equal to the log of A plus the log of B. Okay, so the log distributes over A and B, but converts the multiplication into addition. Okay, so that's just a property of logs, which I won't prove for you right now. But that's exactly what I made use of above. And so basically, what you get is this really interesting effect where the fact that you multiply by the factor 2 can actually be pulled out, and it's additive to the rest of it. Okay, so let's bring in that 10 again. So now we multiply both terms here by 10. So we get 10 log 2 plus 10 log I1 over I naught, and the 10 log I1 over I naught, well, that's just beta 1, because that's the intensity in decibels of just one alarm. Okay, and we saw that above. All right, but what's this piece in here? Well, this is the extra piece. This is how much the intensity increased by doubling the number of alarms that you had. So what's that equal to? It's equal to 10 log of 2, which you could just do on your calculator, and it turns out to be the value 3. Log base 10 of 2 is 0.3, multiply by that by 10, and that gives you 3. And so we get this really interesting effect here, where you have the intensity of just one bell as being 30, and then by doubling it, all you do is you just add 3 to it. You don't multiply by 2, you add 3. And now, why are you adding 3? Well, because the multiplying by 2 was converted by the log into adding 3. Okay, and so your final answer is going to be 3 plus whatever beta 1 was, and beta 1 was 30, and so that tells you that it's 33 decibels. And so you get this really interesting and unexpected answer that one alarm has an intensity in decibels of 30 decibels, whereas two alarms has an intensity of 33 decibels, not the 60, which would have been making the mistake of treating a log scale like a linear scale. Okay, so I went kind of slowly over that, but you should start to see a pattern very quickly here. Okay, if I have four bells, remember that for one, we have beta 1 is equal to 10 log to the base 10 of I1. Okay, but if I have four of them, well, instead of I1, I'm going to have four I1s, like that. Okay, because I've quadrupled the number of bells. So I went from I1 to four I1s. Okay, now once again, you can just pull that 4 in front and you have I1 over I naught, 4 times I1 over I naught, and the multiplication there is just turned into a division, into addition. Okay, and so what winds up happening is you just get that beta 4 is equal to whatever beta 1 was, that's the 10 log I1 over I naught, plus this 10 log 4. Okay, and if you do that on your calculator, you'll just get the number 6. Log to the base 10 of 4 is 0.6, multiplied by 10 is 6. And so for 4 alarms, you actually have 36 decibels. If you do this for 8, well, it's the same story all over again. Okay, so just replace I1 with 8 I1s, because now you have 8 of them. And that 8 will become a term out in front because the log will distribute over the multiplication and turn it into addition. And so you're basically going to have that beta 8, that is the intensity in decibel for 8 bells, is going to be 10 log of 8, like that. And that turns out to be 9. Okay, so it's going to be 9 plus 30, and so you get 39. All right, now we can actually just put this in a table like this. And so here I have the number of alarms, and I have 1, then it goes to 2, 4, 8, 16, 32, 64, and so on. Okay, and notice that each time I go from one level to the next, I'm multiplying by 2. So I have twice as many as the previous level. Okay, but over on this side in the decibel, you're not multiplying by 2, you're adding 3 each time. Okay, so 1 alarm is 30, 2 alarms is 33, 4 alarms is 36, 8 alarms is 39, 16 is 42, 32 is 45, 64 is 48, and so on. Okay, and you could see that what the log function did is it turned this multiplication on this side into an addition in that side. All right, and so actually working in logs is not that hard. Log scales is not that hard. You just have to figure out that like what doubling refers to in terms of addition. Doubling turns out to be adding 3. Okay, and so you could do this for like tripling, quadrupling, 5 times. Each one will have its own additive term. Okay, and so we're going to do one more example here. Let's take a look at. Whoops, I'm clipping it a little bit. Let's take a look at doing the same thing, but now we're going to have 1 bell, then 10, then 100, then 1,000. So we're going to increase it this time by a factor of 10. So beta 10, that is the decibel intensity of 10 bells, is going to be 10 log of 10 I1s. Okay, and again, the log converts the multiplication there into addition. And so you're going to have basically the I1, just I1 beta for I1, which is the 30 decibels right there. But then if you do 10 log base 10 of 10, you get 10. Okay, so how did that work? Well, log base 10 of 10 is 1. Multiply that by 10 and you get 10. 10 plus 30 means that it's 40. So with 10 bells, you have 40 decibels. For 100 bells, you're going to have instead of I1 here, you're going to replace that with 100 I1. And so then you're going to have 10 log of 100. And that's 10 log of 100 is 20. 20 on top of your base 30 gives you 50. Okay. And so you get another interesting little chart. Whoops, went a bit too far here. Another little interesting chart where if you increase the number of alarms you have by a factor of 10 each time, so you go 10, 100, 1,000, 10,000, and so on. It's like adding 10 to the number of decibels. So 1 alarm is 30, 10 alarms is 40, 100 alarms is 50, 1,000 alarms is 60, 10,000 is 70, and so on. 100,000 is 80, and so on. Okay, so there you go. Okay, now I did it for 2. And I also did it for 10. You could try the same thing and see what pattern you get for, say, tripling at each time. So you would have 1 alarm, and then at the next level you would have 3, and then 9, and then 27, and so on, and see how much you increase your decibels each time you triple the number of alarms you have. You could do it with 5. You could do it with any factor you like, okay? So we did it for 2 and 10, and you can expect maybe on a test to see it for some other factor. So it's worth your while trying to work this out for some other factor. All right, there's the story with decibels, and just to remind you, this is basically a log scale. And so it's useful whenever you have things that are spanning many, many orders of magnitude. And certainly humanly audible sound spans many orders of magnitude. And so using a log scale there makes a lot of sense. pH, if you're in chemistry, also does the same. If you're in finance and you're trying to compare millionaires and billionaires, well, then it makes sense to put even financial amounts on a log scale. Okay, so log scales come up quite a bit. And the essential thing to remember about a log scale is that they're not additive. And so it's not like you have like one sound which is 30 decibels and another sound which is 30 decibels. And you put the two sounds together and you get 60. No, 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 no. We just saw that you have 30 decibels and you have another one which is 30, and you put them together and you get 33. Okay, not 60. And it works like that even if they're not the same. So if you have one sound which is 40 decibels and another one which is 30 decibels, you put them together, it's not 40 plus 30. It just doesn't work out that way. Okay, so the decibels are not additives. The I's are. Okay, so if you have one sound source which is 5 milliwatts per meter squared, another one which is 10 milliwatts per meter squared, 5 plus 10 is 15, and so the combined is going to be 15 milliwatts per meter squared. Yeah, I's will add, but not the betas. All right, that's the story with decibels. The last thing we're going to study, whoops, went a bit too far. The last thing we're going to study with sound is the Doppler effect. Okay, now the Doppler effect does occur with other waves besides sound, but the formula I'm going to give you is going to be specific for sound. Especially, it does not work for light, because for light you have to use a different formula which takes into consideration special relativity, and that's beyond the scope of this course. But we can study the Doppler effect for sound, and we will. What is this Doppler effect? And you've probably heard it. You've probably heard it. Whenever you have like a car and it's blowing its horn as it drives past you, you can tell that the frequency changes as the car moves past you. And it's this characteristic sound where it goes from high pitch to low pitch as the car passes you. So it makes a sound something like this as it passes by you. Okay, and this is known as the Doppler effect. It's important in a lot of diagnostic tools. For instance, we have ultrasound. Now, regular ultrasound just looks for reflections from within the body of sound, but you can have Doppler ultrasound, which looks at velocities of things that are moving in the body. So you can actually use Doppler ultrasound to measure how fast blood is flowing through your heart or something like that. Okay, so this is the Doppler effect. It's also used, and now this is with radio waves, so it's not sound, but this is how police radars work to tell how fast you're moving. Basically, the police radars will look at the frequency shift as the car moves, and that frequency shift can be used to calculate how fast the car is going. Okay, very accurately, actually. Okay, so basically, Doppler effect, when a sound source or a receiver, doesn't matter whether it's the source or receiver, are moving, then the frequency that you hear is different than the frequency that's emitted. Okay, and there's actually 4 possibilities for this, so let's go through those 4 possibilities. One is this one, which is the most common one, the receiver standing still. Okay, so here's the receiver, that's you listening, and you're not moving at all. All right, and here's a sound source, say a car, and the car is moving towards you in this particular example with some velocity, and it's emitting these waves in front of it. Okay, and the waves that it's emitting have a frequency f0, but that's not the frequency you're going to hear. So the emitted frequency is f0, and you're going to hear another frequency. If the source is approaching you, you're actually going to hear a higher frequency than the emitted frequency, okay? And so as the source comes towards you, you actually hear a higher pitch than what's actually being emitted. If you wonder why that's happening, and it's not hard to drive, but I'm not going to drive it for you. If you want to see it, you can just look on the Wikipedia page. The derivation's actually pretty short, but it doesn't really add too much to the intuition and what's going on. Basically, you can imagine that you've got here's a car, and it's emitting these sound waves, and it keeps emitting them. Okay, and so suppose it's standing still, and it emits a sound wave, and here's the crest. It gets to there before it starts to emit another one. Okay, so that's the wavelength right there, because the first crest got this far before it started emitting another one. But now, what if the car is moving? Well, not only did it emit one, and it's traveling, but the car is also moving forward behind that wave, and then it emits another one. And you could see, because the car moved forward, it's a little bit closer to the crest that it just emitted before it emits the other one, and so it's shrunk the wavelength. Okay, now if you get shorter wavelengths, so the wavelengths are kind of compressed in the front of the car. If you get these shorter wavelengths means higher frequency, and therefore the frequency that you're going to hear is higher than the frequency of the being emitted by the source. Okay, and so when a source is approaching the receiver, the frequency you hear is higher. That's also true when the receiver, when the source is standing still, and you as the receiver are running towards the source. Okay, so here we have the source standing still, and it's emitting a frequency f0. Here you are the receiver, you're running towards the source, you're actually going to hear a higher frequency. Okay, now why? Well, now because these crests are coming at you, but if you're running into the crests, you're going to run into them faster than you would if you were just standing still. So if the crests are getting at you at a faster rate means a higher frequency, therefore you hear a higher frequency. So if the receiver is moving towards the source, you hear a higher frequency. If the source is moving towards the receiver, you hear a higher frequency. And if both are moving towards one another, then they both help one another out to even increase the frequency more. Okay? Now, what happens if you're moving away? So if the source is moving away, well, now the same effect that I had before, but now, this wave is being emitted, this wavefront is being emitted, but at the same time the car is moving away, and so it's actually stretching out the wavelengths. Longer wavelengths are lower frequency, and so if the source is moving away from the receiver will hear a lower frequency than what's being emitted. Okay, and similarly, if the receiver is running away from the source, well, then the waves have to travel further to catch up to this receiver, and so the receiver is receiving them less frequently, and therefore lower frequency. Okay, so there's actually 4 possibilities. You can have the source approaching the receiver, you can have the source receding from the receiver, you can have the receiver approaching the source, or the receiver receding from the source, okay, and moving away from the source. And so here's the formula for it, which kind of summarizes it. And now this looks like a little bit of a busy formula. Let me see if I can get it all in there. It is a bit of a busy formula, but I mean, it contains all the possibilities. Okay, so what's busy about it is these pluses and minuses, which you have to get right, otherwise you'll get the wrong answer. And so let's go through it. That f0, that is the frequency that's emitted. That's the frequency you would actually hear if the source were standing still and the receiver is standing still. So if you're just standing beside this car and it's got the horn blaring, and you've got some device which can measure the frequency, you would get the actual frequency that's being emitted. Okay, now if either the source or the receiver are moving, or both, you're going to actually detect something different than what's being emitted. And so the observed frequency, that's just plain old f. Okay, and so that's the frequency of what you actually hear. All right, now there is the speed of sound. Okay, that's V here. You can see it there and there. Okay, both on the top and the bottom. That's the speed of sound. Now, the speed of sound does vary a little bit with air temperature and so on, but for the purposes of our course, we'll just set the speed of sound to be we'll say the speed of sound is 340 meters per second. That's very close to being correct. I mean, it might get as low as 335 meters per second if at hot temperatures, and so it varies. All right, VR here on top in the numerator, that is actually the speed of the receiver. Okay, and Vs, that's the speed of the source. Okay, and both can be moving. All right, both the receiver and the source can be moving. And now you've got the plus and minus on the top and the plus and minus on the bottom. You go, well, which one do I use? Okay, so here's the rule, and it might be confusing at first, but I'll show you an easy way to remember it. You would subtract V minus Vs if the receiver is moving away from the source. So if the receiver and the source are moving away, sorry, if the receiver is moving away from the source is standing still, the receiver is moving away from the source, you would use the subtraction on top, okay? Conversely, if the receiver is moving towards the source, you would add, all right? Now on the bottom, it's the other way around. You would add if the source is moving away from the receiver, and you would subtract if the source is moving towards the receiver. Okay, so they're actually opposite. And I tried to indicate that because on top I have minus plus, and on the bottom I have plus minus. And now at this point you go, geez, I'm going to confuse this. And it is easy to confuse, okay? But the easy way to do this is to just think to yourself, do I want a higher frequency or a lower frequency? Okay, so I think it's pretty easy to remember that when source and receiver are just approaching one another, you expect a higher frequency, and when source and receiver are moving away from one another, they're receding from one another, you expect a lower frequency. And so you know what? Just choose a sign that will give you your expected answer, and that helps to, that helps you to remember which sign is the right sign. Okay, and so well, let's do a problem and you'll see how that works. Okay, so we have a car, and it has a horn which emits a sound of 500 hertz. So that's your F naught. Okay, that's the sound that's emitted and would be observed if neither source nor receiver were moving. Okay, now if the car is approaching you at 100 kilometers per hour while you're standing still, what frequency do you hear? Okay, so let me say that again. So if the car is approaching you while you're standing still, what frequency do you hear? And the car is moving at 100 kilometers per hour. Now, if you wait a while, the car is obviously going to pass you, okay? And then it's going to travel in the other direction. It's going to recede away from you. It's going to move away from you at 100 kilometers per hour. Now, what frequency do you hear? Okay, so in part A, it's moving towards you, and then it passes you, and then in part B, it's moving away from you, okay? And then in part C, I say, you know what? Just repeat the previous two. But instead of the sound source being the car moving, the car's standing still. And you're going to be moving, okay? Now, I mean, you can't run at 100 kilometers per hour, but maybe you're in a car, okay? And you're listening, and you hear this car that's stationary on the road. This is the source, the car that's stationary, and it's got its horn blaring, emitting this 500 hertz sound, and you're driving towards it. What do you hear? Driving towards it at 100 kilometers per hour. And then you pass it and you're moving away from it at 100 kilometers per hour. What do you hear? Okay. And then finally in part D, to show you that you could have both the receiver and the source moving, I said to you, okay, well, what if they're both moving at 100 kilometers per hour away from one another? Okay, so let's do this problem. All right. So first, let's convert the 100 kilometers per hour into meters per second, because our speed of sound is 340 meters per second, and so we need to work in meters per second. And you remember that was easy, you just divide by 3.6, and so you get that for part A, the car, which is the source, is moving at 27.8 meters per second, rounding off. Okay, and so here's a diagram. You have the source moving at 27.8 meters per second towards the receiver, which is just standing still. Okay, and you expect in this scenario for the frequency that's heard by the receiver to be higher than that 500 hertz. Okay, and so in order for that to happen, you have to subtract in the denominator. If you added, you would get a lower number. And so by subtracting in the denominator, you'll get a bigger number. Remember, a smaller denominator makes for a bigger answer. Okay, so because you're actually looking at the denominator there for the source, you actually want to subtract. So the receiver isn't moving, so VR is 0, so that drops out. That makes that one easy. But VS is in the bottom here, and you go, well, do I want a plus or a minus? You put a plus there, and you're going to get less than 500. That's wrong. Okay, and so you put a minus in there, and so you get 340 divided by 340 minus 27.8. Okay, so there's your V's and VS, and multiply that by 500, and you get that you would hear 544.5 hertz. Okay, now that's significant. Okay, that's definitely it's not quite 10%. 550 would be 10% higher. It's a little less than that, but still, this is definitely something that you would hear. Okay, it's like 9% higher. Okay, so that's definitely something you would hear. All right, now in the next one, the cars pass by you, so now the car is receding, it's traveling away from you, and so you're still standing still as a receiver. VR is 0, but the source is now moving 27.8 meters per second, but it's moving away from you. You expect to hear a lower frequency, and in order to get a lower frequency, you must add in the denominator. You must have a bigger denominator, not a smaller denominator. So above we had minus, but now that's become a plus. Plugging in the numbers, multiplying by 500, the emitted frequency, and you get 462.22 hertz. Okay, so again, something that you would definitely notice. And so you hear that characteristic sound when it's approaching. As it's approaching you, it's high frequency, and then it drops to low frequency. So it goes that kind of a sound. Okay. All right. So in part C, I said, you know what? Repeat this. But now let's have the source standing still. So this car just blaring its horn, emitting 500 hertz. But you are, and I'm showing you running here, but you can't run at 100 kilometers per hour. But you're approaching the car at 27.8 meters per second or 100 kilometers per hour. Again, because the source and receiver are getting closer, okay, you expect the frequency to be higher. And so how does that work? Well, now VR is in the numerator, and in order to get a bigger number in the numerator, you have to add. And so if you think about this, it's got to be V plus VR. Okay. Again, you could say, well, I'll just do the subtraction, and you would get a lower number, and then you know that you did it wrong. Okay. So yes, it's plus. And VS is 0 because it's not moving. So in the denominator, the VS just drops out. So you just have VR in the numerator there. And so if you have, so you just plug in the numbers, 340 plus 27.8 divided by 340 times 500, and you get 540 hertz. Okay. And that's with the receiver approaching. What if the receiver is receding, or the receiver is moving away from the source? Well, then it's the same thing, but now you have to subtract because you expect a lower number. Okay, expect the frequency to lower, and sure enough, it does. It's 459.1 hertz. Okay, and so there you go. You get a drop in the frequency. And finally, in part D, I just said, you know what? Let's suppose that they're both moving away from one another, and at 100 kilometers per hour. And so VS is 27.8, VR is 27.8. Both of them are conspiring to lower the frequency. Okay, both of them. So on top, you want the subtraction to lower the frequency. On the bottom, you want the addition to lower the frequency even more. And so when you substitute those numbers in, you're going to get a very low number, 424.4 hertz. Okay, and so this is the story with Doppler effect. Again, Doppler effect is kind of important because it's used in a lot of medical diagnostic equipment. Well, I don't know about many, but some diagnostic equipment, such as the Doppler Ultrasound, which is a very easy way to measure how fast the blood flows through the heart. Okay, I mean, you don't want to be sticking probes in there. Okay, so it's kind of a very useful tool. Just like a police radar can tell how fast you're traveling using Doppler on radio waves, ultrasound can tell how fast blood is traveling through the heart using Doppler shift sound waves. Okay, this is the end of this lecture.